Hey everybody, happy Wednesday / Thursday. I'm filming this video after the lesson you went through today on the volume of solids, volume of prisms and cylinders. That's what we'll do in this video, is what I have here starred in red, the volume of prism, volume of cylinder. We'll get to surface area later, I think on Friday. So I actually want to begin talking through cylinders first. Make sure you got the formula down for that. I'm going to tell you a few other things here. So I'm going to use the idea of this being kind of an example of a cylinder that I'm trying to demonstrate for you guys here. So prisms and cylinders, pretty much freaking the same thing. The only difference is what their bases are, okay? So definition of prisms or cylinders, I guess here, is we just have to have congruent bases that are parallel to each other, okay? That might present itself like this, okay? And this would be, the most specific I could call something like this would be, well, what is my base? My base is a circle. So that would mean I'd have to be a cylinder. Remember, cylinders are non-polygonal. They're curved bases. Okay, now I have congruent circles because what are these? You guys know what these are? These are compact discs. CDs, that's right, CDs from the 90s and 2000s, I think. I think the most recent I bought one was like 2012 maybe, but probably more like 2010. But anyways, I have CDs here. So I stack them all up. They're going to be from our demonstration. So I could have my cylinder like this where I have congruent bases and I have a given height. Or a given height here, which is just how many CDs I have, I guess, here. But anyways, I have that. So if I have it like this, if my bases are immediately above one another, like I drop a perpendicular from the edge, any of the edges of this base here, if I drop a perpendicular and it hits the other edge of the other base right here, that's something called a right cylinder, or a right prism here. So notice here, if I go from one base to another base and I draw from the edge of one of the bases and I drop a perpendicular in, I hit the other edge of the other base on the other side. And that's true for over here too. I could count those as my bases if I want. But anyways, I'm talking about these ones here. So I can either be a right cylinder like this, okay? So if I'm pretending this is all a solid, right? I don't have a hole in the middle, so ignore the hole for the compact disc. Okay, I can be a right cylinder, or I can be something called an oblique cylinder. Okay, so we'll put that in oblique cylinder as well. And yeah, that's if we got something like this going. If I take my discs and I slant them a bit, okay, so now, look at that here. What does that look like? Well, this is actually technically still a cylinder. It's sort of like something sinking over. It's kind of like going over here. But my two bases are parallel to each other. And that's good, and they're congruent. So it actually fit the definition of a cylinder. I have two non-polygonal shapes that are circular or curved. They're not polygons, and they're parallel to each other. They're congruent. So it's everything connecting the bases, and in between would be the solid. That's something called oblique. Okay, so let's start by actually drawing that into our toolkits so we get some examples of these things here. And then we'll come to the formula. And we're going to ask ourselves, is the same for a right cylinder as it is for an oblique cylinder? So I could have drawn these in, and you could have just had them there. But I want to do this with you because I think actually drawing this gets you thinking and gets you realizing some things about the shape. So please draw them in along with me. Okay, I'm going to draw my cylinder, and I'm going to try to do it so it kind of resembles a circle. Okay, if you see it from this angle here, this is a circle. It doesn't look like it looks like an oval to you, but no, it's a circle. It's a circle base here. Okay, so I have congruent. When I draw these, I draw my bases first. Okay, that's what I do here because my bases should be congruent. Okay, should be congruent here. So I got congruent bases. I'm going to see about that, and then it's going to be dashed because the rest of the solid's going to be obscuring the behinds here. So then I'm going to do the side. This is something called a lateral edge. I mean, I guess there isn't an edge here because this is curved the side here. So this is just a lateral height, I guess, here. Lateral, left, right, that kind of thing here. So I got my bases, and then I got my lateral here, okay? And I tried to do this at a right angle, okay? I tried to do this at a right angle here. And I might put the right down here. I recommend maybe you do it too. Put a right angle there, put a right angle there, put a right angle, like they're come down as right angles here. What this is going to be called, most specific name I have for this is a right, okay, this is a right circular cylinder. Okay, so again, I said in class, and it's a lot of information, cylinders don't have to be circles. They just have to be curved, okay? So they could be ovals on top, okay? But I try to do it like a circle here with a particular radius, okay? And because the bases are congruent, I can do this. I can tick mark there, tick mark there. The radii in both of those congruent circles, they got to be congruent to each other by definition of congruent circles. So I have the radius there, okay? That's a right circular prism. I also want to talk about this in the video. This is going to come up on your Thursday classwork, and that's going to be if I draw an oblique cylinder. That should be a word that you guys know. That'll come up on Thursday's classwork. That's if I have two congruent bases that are circles or circular or non-polygonal like this here, and they're parallel to each other, they're congruent, but if I draw from this edge and drop a perpendicular to the plane containing the other base at a right angle, right, a perpendicular, I don't hit the edge of the other circle. So I wouldn't do that here. Obviously, if I'm going straight down through here, I'm not hitting the edge of this one here. You see my Modest Mouse album there, I guess. College, man, Modest Mouse. Everyone listens to that stuff. At least when I was in college. All right, so let's check it out here, and I'll draw an oblique one out. So same, that could be the same exact deal. I'm gonna try to do it. I'll try to do it with the same exact type size circle. Draw it like this, or whatever. We'll say that those are congruent. Okay, I got R here, but it's oblique, so this is gonna be offset. Okay, offset over here. So I'm gonna draw my other circle down here. Be obscured by this action here. Oh, you know, I didn't draw it. I drew that too big. Here, I do it smaller. It's got to be congruent. So I'll try to draw it accurately, where it's looks like it's about the same size. It's kind of harder to draw the oblique thing because it's not right above the other. Okay, I think this might work. Let's see here. It's hard to draw this, isn't it? There we go. Just go straight line. There we go here, and there we go here. Okay, so this would fit the definition of an oblique circular cylinder. If, again, I have congruent bases, so here, we'll say that's R, and we'll say that these are all congruent together. But anyways, these two bases are congruent. And it's oblique because if I drop a perpendicular here, I'm not going to hit the edge like I did in that one. So if I drop a perpendicular here, oh, it looks like it's going to go to the middle of it. I don't want to do that. Maybe I'll do the perpendicular from the outside here. Okay, I don't actually hit the edge of the base that we have down there. So that's why it's going to be oblique and not a right cylinder here. Okay, so that's oblique. And yes, let's generate a formula for this, shall we? Let's get the volume formula actually for both of these guys here. And this is where it connects to class today, okay? So what we talked about in class, the thing that I really want to get you across in class today is thinking about volume. And you know you have solids, right? You have solids here. Let me figure out, let me get an exact cylinder here, right? How much do I fit in here? Well, how much do I fit in here? Well, I want you to think of solids and their volumes as layers here, okay? I have a layer that's equal to, well, what's going to determine my layers, how big it is? Well, it's going to be the freaking base. Okay, going to be the freaking base. That tells me how large one of my layers is. So when we did the one that was, 105 in class, we had a layer that was 35, right? 35 of those faces that we saw, those little squares. And so we knew that first layer was 35 cubic units. And then there were 3 deep, so we multiplied by 3, we got 105. So here, I want you guys to think of volume as layers, actually, of area. Layers of area here. So imagine that you're just running planes through this and stacking it up, and you're filling up, right? Filling up water, filling it up to the top. What determines how much volume we really need is 2 things. The base, how large your base is, right? And how far you go. And that's called the height. That's called the height. So if I had a base of 35 units like we did in class, and I had a depth of 3, I would say the height for that, right? My perpendicular would be a height of 3. All I got to do is base area times by the height, and you got the answer. And the same thing is going to be true for cylinders, right? Cylinders as well. Check it out here. I'm going to think about this in the context of the little compact disc, of the CDs that I have here, okay? So I want to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and how about I got 15 CDs right here, okay? So if I think of each of these as a layer, okay, I'm going to think of it, pretend that these are infinitely thin. Obviously, this has volume. This is a cylinder in of itself, okay? Just a very, very small thing. I'm going to think about this, and this will come up in tomorrow's classwork, in Thursday's classwork, Each one of these, think about your base as being a thin layer of area, okay, of area. It's pretty confusing here. I take this area, let's be this circle, and it's called one compact disc. How do I get the volume of this entire cylinder that I'm trying to demonstrate to you? Well, we take the base area, what we have here, and then, right, we got to multiply by how much height we have, how much that'll fill up the whole thing. So obviously area doesn't have height necessarily, but right, we got to think about how large our thing is here too. We got to multiply that base area by something, and height is the logical thing. Something, if I had more CDs here, I would take whatever my top CD is, and I'd have to multiply by higher, right? I have to multiply by whatever the area of this is, times by ever how many CDs I have, and I would say that is the volume, right, in terms of number of CDs, okay? 15 right here, okay? So anyways, my whole point of what I'm trying to get to this is that the volume for cylinders is going to be the same as prisms. And I might put the prisms formula in for you because I went over that a little bit today, okay? Rectangular prisms, you know that's length times width times height, but a more broad formula for you is going to be V times by capital B times by lowercase h, okay? What does the capital B mean? The capital B means base area, okay? B equals base area. Okay, it's capital B because you have to do a calculation to get it, to get the base area of something. Length times width for a rectangle, or for if you have a triangular prism, then it would be 1/2 the base dimension, right? Lowercase b times by lowercase h, okay? B is base area and h equals the height, okay? The height you gotta go, okay? So remember your bases are your congruent figures that are parallel to each other, in parallel planes here. So anyways, volume for cylinders is going to be the exact same freaking thing. Exact same freaking thing. And I actually can come up with this more than one way, because if it's a actually, you know what? I want to come up with a different thing. Okay, circular cylinder. Because on the classwork that you had today, that very last question isn't a circular cylinder, but it is a cylinder. You have to use that formula. Okay, circular cylinder, I can come up with a more precise formula, okay? Circular similar volume, getting kind of close here. And that is what? Well, base area. So if I had to figure out, I have 15 of these. That's my height. Where do I start with? How do I figure out how much is in one layer? Well, one layer is really determined by its area, by the base area. And within this, okay, and the classwork goes into this, within this, you'd have things called cross sections that are freaking congruent, would have the same radius here. So you're basically taking one base and then multiplying it by the number of cross sections you have, which is the height, right? Our height here, our perpendicular height. And my height is actually right here of the oblique one. Okay, the oblique one is my height on. You get that on the outside. It's just the perpendicular between the two planes containing the two congruent, well, in this case, circles, because these are circular cylinders here. Okay, so formula for this, let's get into formula filled in. It's V equals, okay, for a circular cylinder, we can get it more specific because actually base area of a freaking circle, my bases are circles. What's my formula for the area of a circle? Let's maybe rewrite this because sometimes it appears like that. It's going to be the same thing as is up here is for cylinders. But what I can do is I can create a specific one for circles because what do I know about the base area, or what do I know about the area of a circle? What's the formula? Pi r squared. Thank you so much for saying that in front of the whole class here. Is pi r squared times by h here, okay? So getting the volume of a right one, I think you can all agree with me, would be, well, I got 15 CDs right here for a right cylinder, again, at right angles right here. What about an oblique situation? An oblique situation like this here, if I change this and all of a sudden my bases are no longer, they're still parallel to one another, therefore they're still a cylinder, but they're no longer, when I drop a perpendicular from the edges, it no longer meets along the other edge of the other base here. If I slide it this way, is what I'm trying to say here, okay? Does my volume change? Does it change? My volume, how many, I had 15 CDs to start with, make it oblique. How many CDs do I have now? Oh, I almost dropped some, okay? No camera tricks though. I still have 15 CDs. Did my volume change at all? No, okay? So these guys both use the same formula, Okay, both use the same formula for volume here too. Okay, and then the same thing is gonna go for prisms. Okay, 4 prisms right here. Let me get you a few prisms we can look at here. I got a triangular prism right here. This, obviously, these are the same height. Check it out here. These are the same height as one another. This one here clearly fits in more stuff than the triangular one would fit in. Why? Why does the rectangular prism fit in more stuff, would have more volume than the triangular prism when they have the same freaking height? Well, the bases. Look, okay, so the base is larger on this rectangular prism, so it's going to have more volume here. So the things that determines volume, how much you put in, it's not length times width times height. It's the base area of whatever shape it is here. You just got to multiply it by the height, and that tells you how many cubic units you can fit into it here, okay? That's in here. That's going to be true for any prism, okay, for any prism. And that's true, same thing, too, for right prisms, okay? So let's draw on a right prism together. Boom. There we go. Well, it doesn't have to be I'm doing a right rectangular prism right here. So anyways, well, that's a right rectangular prism, okay? So let's do it here. So that means this comes at a right angle right there. That's the significant thing, to be a right prism, okay? And then we're drawing in together. I got to make it do it so it looks congruent. I think I went too far there. Okay, I'll go to the side here, and then drop in. So in your classwork tomorrow, you're going to have to draw some of these. Okay, the key thing is bases are congruent. Okay, bases could have been over here too, right? Those could have been bases too, congruent bases here. It's all good. So another word for a prism is something called a parallelepiped. Parallelepiped, that's a more official name for a prism because it's parallel. They're the top and bottom. Well, actually, it's top and bottom are parallelograms. Anyways, that's more specific than a prism itself. But the two planes are parallel also that contain the bases. Okay, so anyways, this one is right. This is right rectangular, right rectangular is what I have here. But the key thing for it being right is that if I draw between the edges, okay, this edge of this base to this base, if I draw a perpendicular, I hit the other edge of the other base here too, okay? Base area, okay, that's B. This is H, that's height. Okay, that's height right here. Okay, and this formula still works. If I have a certain amount, right, base area is here, find it, multiply that base area. So it includes everything on the inside. It includes all these cross sections here. Base area times by height. That's going to be true for a right prism. But what if I moved it? Okay, what if I moved it? I had some baseball cards. Let me get you my baseball cards right here. Mr. Forden going back down to, I don't even remember, Rafael Palmeiro, Trot Nixon. Who are these people right here? This is it. This is what it's all about. Mr. Forden's like 1990s baseball card collection, which I meant to have out, okay? I'm only going to pull out a few cards for the sake of time. I meant to have it ready to go, okay? So, right, I got myself, that would be a prism, right? And it's kind of at right angles. Let's say this is my top here. We got Jeff King. I don't know if I remember Jeff King. Oh, yeah, mustache, though. This is a sweet mustache right there. That's the 90s, baby. All right, so anyways, my volume here, 1, 2, 3, 4, 5. Let's say it's 5 cards, okay? 5 cards here. Does my volume change at all? Okay, does my volume change at all if I go oblique? Okay, if I go oblique, meaning I still have congruent bases in those parallel planes here. This is three cards, what? 3 cards below this one? All right, how many cards did I get here? I got 5 cards. So it's 4 cards below this one, okay? So congruent bases and everything in between. Does my volume change if my bases are not right on top of one another? No, it doesn't, because it's still the same base area and it's still the same height. I still have 5 cards right there, okay? So oblique prisms have the same volume as the right prisms do. And same thing for the cylinders. Oblique cylinders have the same volume as right cylinders do here. Let's draw an oblique cylinder. Sorry, an oblique prism for us here. So I'm going to do a little offset. Okay? Going down here maybe. Sure. I'm just going to draw the same thing again. And here. So boom, boom. There we go. Got to do it so it looks kind of congruent. A little further. We go here. Boom. There we go. There we go. They're congruent right here. It's oblique. But you know what? The height isn't going to be this lateral edge. These are called the lateral edges here. We're not even really going to go over that vocabulary this year, but who knows? Might come up in your future. Who knows? Okay. And here, right, your height would still be the perpendicular between the two planes. Okay. Base area times by height would be the same way. It would still get there. If you tilt over, leaning tower piece is tilted over, but it would still have the same volume if it's standing straight up, okay? And speaking of the Leaning Tower of Pisa, that was in Italy. An Italian mathematician, Bonaventura Cavalieri, is the one who's credited that with that assumption. It's basically a postulate that if your prism or cylinder is oblique, you still use the same formula. You just need to know what the height is. And remember, the distance is calculated by the perpendicular between things. And the perpendicular between the planes containing those congruent bases in this situation right here. Okay? So there it is right now. Hopefully it's laid out. You'll get some practice with it in your classwork today. But hopefully you have these volume stuff written down here. Volume equals B. Why is it capitalized? That's base area times by height, which is one dimension. Base area, it would be 2 dimensions. Times by height. And that's why height's lowercase, it's only 1 dimension. Circular cylinder volume, pi r squared h. Why? Well, the base area, because it's a circle, has to be pi r squared. H, well, that's the height. Okay, that's the height. That's how many of those bases we could fit in from one base to another. We just got to multiply it by how much height are we talking? That's it here. Okay, thank you for watching. I'm going to show you right now. Let's see here. Let's flip back over to Mr. Fortin's gone away. A little bit here. These are kind of some slides I was going through earlier here, just to remind you, and I don't think I can turn on my camera. I wish I could. Oops. I'm looking at people's answers here. Boo. A lot of people already done it. So just to remind you guys, there we go. All right, show somebody thing. That was my thinking on that one actually here. So I just did this with 7th block earlier here too. Check it out here. How do I get this? V equals base area times by height, okay? So this is what I said in class, and hopefully you're paying attention and getting this. This here would be exactly half as much as a prism that would have a 3 by 3, right, type base to it, okay, right? If we picture this, right, this volume, this should be just half as much. Reason? Base area. Half as large as the base area if it were a 3 by 3 square. So a 3 by 3 right triangle, okay, goes by different formulas. So volume on this one, base area 1/2, 3 times 3 times by height, which is, looks like we have 1, 2, 3, 4 slices, 4 layers, and that will get you to 18 units here, okay? So this was supposed to get you to show you it's really just the base area. That is the key difference here that you need to consider if your height's the same as some other shape here, okay? All right, same deal here. We can totally apply this. Well, how much is in that top circular disc? Pi r squared. How many of them do you have? You have 3. There you go. You can answer that one out here. And then finally, this one here. Don't know calculus, or you're not sure how to do integrals and whatnot here, and integration, calculating the area of this freaking curve thing right here. So anyways, how would you do this? Well, you'd have to know what the base area is and multiply it by the height, okay? Because, right, they have cross sections that are all identical to this base area, all in between. And how many of them do you have? Well, whatever the height is how many cross sections you have. Okay, that's the video. Hopefully this was a little bit helpful here. And yeah, thank you for watching. Have a wonderful Thursday. Classwork is going to reemphasize a lot of this stuff that I kind of went over in this video here. Have a wonderful day. Message me if you have any questions. Take care. Bye-bye now.